This lesson is for FST, Lesson 7.6 on the fundamental theorem of algebra. The first topic is multiplicity of a polynomial is the highest power that it can possess that appears as a factor of that polynomial. So let's look at our example here. It'll make more sense once we try it with some numbers. If we have x plus 1, that's one factor, and then we have x minus 3 to the third. What that really means is we have x plus 1 as one factor, and then we have x minus 2, and that factor appears 3 times. The zeros that would have come from these factors would have been a negative 1, and this one would have been a 2. So there are 2 zeros, but one of them appears 3 times. The 2 here has a multiplicity of 3 because it appears 3 times. So total then we would say we have 3 zeros here and 1 zero there, so it has a total of 4 zeros. The reason why it has 4 is because we have a multiplicity of one of them being a 3. So that 0 is actually there multiple times, so that's why it has a multiplicity. If we were to go ahead and multiply all of these factors together, we would end up with an x to the 4th power as our polynomial, and usually the number of zeros matches with the degree. So this has 4 zeros. The zeros are negative 1 and 2 has a multiplicity of 3, meaning that it appears 3 times. The other topic for today is on zeros of quadratics. Remember that a quadratic is a degree 2. And so when we talk about how many zeros a quadratic will have, there are 3 different possibilities. A quadratic, which forms a parabola when graphed, could have a situation where the parabola doesn't cross the x-axis at all, so it has no zeros. There is a situation, however, where that parabola could just touch the x-axis, and so that would have 1 zero. And then the one that students are probably the most familiar with is when the parabola crosses the x-axis twice, and so that would have 2 zeros. So again, keep in mind that the degree should match with the number of zeros of a particular polynomial. So that's what the fundamental theorem of algebra is saying, is that when you have a polynomial with a degree greater than 1, it's going to have at least one complex zero. So if you have complex coefficients going on in your polynomial, then you're going to have at least one of those being complex. So we're going to utilize that to find all the zeros in a polynomial. So the first type of situation you're going to run into is one like this first example. It's actually book example number 3. You've got polynomial p of x, which is 3x cubed minus 2x squared plus 12x minus 8. They're asking you to verify that 2i is a 0. So they're giving you one of the zeros. So to verify that it is a 0, we should plug it in for x, and by the time we're done calculating, we should get the number 0 back. So we're going to plug the 0 into the polynomial. So I'm going to take the polynomial, and wherever I have an x, I'm going to leave an empty space. And in the empty space, I'm going to put the 0 that they gave me, 2i. And now we deal with the order of operations. So let's see what we get here for the first one. 2i cubed. 2 cubed is 8, and 8 times 3 is going to be 24 there. Now let's talk about I cubed. I cubed is going to be the same as saying I squared times I. And I squared I know is negative 1. So this is going to be a negative 24 because of I squared changes that number to its opposite, and then there's going to be an I there. Now let's move on to the next chunk. The next chunk is going to be subtracted. We've got 2i squared, that's going to be 4i squared, times the 2 in front is going to be 8. And then the I squared, however, is going to turn that back into positive. So I'm just going to say positive 8 there. Then right here, I don't have any squares to deal with, so I'm just going to do straight old multiplication. So I'm going to get 12 times 2 is 24i. and then I've got a minus 8 on the end. Notice what we have now. We've got negative 24i plus a positive 24i. Those are going to cancel, and 8 minus 8, obviously here we get 0, which is what we thought we were going to get. Next item, lots of different theorems in the lesson today, so let's just go through all of them. The number of zeros of a polynomial means that the degree and the number of zeros is always going to match. So that's something that students just need to memorize. The degree and the number of zeros are always going to be the same. The wiggliness theorem is our next one. The graph of a polynomial, if you take that graph and draw any horizontal line through it so that it crosses the graph as many times as possible, that's going to tell you the highest value of the degree of that polynomial. So the number of times a horizontal line can cross a graph is the same as its degree. So if we take this particular example, if I were to draw a horizontal line down here, it would only cross the graph twice. But if I drew my horizontal line further up, it would cross the graph 1, 2, 3, 4 times. So this would probably be a degree 4 polynomial. So the horizontal line crosses through how many times it wiggles, and that tells you the degree. The conjugate zeros theorem next is basically telling you that if you have a complex number that is a zero of the polynomial, then its conjugate is also a zero. So if we go back to the one that we were working on earlier, the 3x cubed minus 2x squared plus 12x minus 8 problem, when we knew that 2i was a zero, then we know that negative 2i is also a zero. So what that tells you is that complex zeros always come in pairs. The complex number itself is going to be a zero, and then its conjugate will also be a zero. Now notice that the directions on this question have changed. Now they want us to factor it. So if they gave us one of the zeros and we know another zero, that means we should be finding 3 zeros altogether. The reason is, this is a degree 3 problem. So we're going to take the 2 zeros that we know and we're going to turn those into factors. Remember that when you have 2 as a zero, the factor that goes with it is x minus 2. Well, the same thing is true for complex zeros. So if I have 2i as a zero, x minus 2i is going to be one of the factors. Remember too that its complex conjugate is also going to be a zero, so x plus 2i is also going to be a factor. Now I'm going to go ahead and multiply those together using FOIL. So when I do that, I get x squared, negative 2ix, and positive 2ix, those are going to cancel. And then for the last terms, I'm going to get negative 4i squared, which is going to turn into positive 4. Negative 4i squared is negative 1, times that negative 4 is positive 4. So now what I'm going to do is divide my polynomial by the new polynomial that I just got. So I got x squared plus 4. I know that those two together came from those two factors. I'm going to divide that into my polynomial. So I'm going to rewrite the polynomial as 3x cubed minus 2x squared plus 12x minus 8. So now I'm going to do long division, and my final answer up top is going to be my last factor. I have 2, I need a third because it's a degree 3. X squared into 3x cubed. So what times x squared is 3x cubed? That's going to be 3x. 3x times 4 is positive 12x. 3x times x squared is going to be 3x cubed. Now I need to subtract both of those. Those are opposites of each other, so that becomes 0. The negative 2x squared is going to drop. And 12x minus 12x is going to be nothing there. So I bring down my negative 8, and now I start all over. X squared times what is negative 2x squared? That's going to be negative 2. Negative 2 times x squared is negative 2x squared. Negative 2 times 4 is negative 8. And when I'm all done there, if I subtract, I am going to get 0. So that means there's no remainder there, and that's a good thing. That's what I was expecting to have happen. So now that's my last factor. So 3x minus 2 is the last factor. And now I'm going to find the 0 that comes from that. So I want to figure out 3 times what minus 2 equals 0. So I add 2 to both sides, divide by 3. My last 0 is going to be 2/3. So here's my zeros: 2i, negative 2i, and then 2/3. So let's talk through that because that was quite a lengthy process. When they ask you to factor and they give you a complex 0, turn that complex 0 into a factor. Know that its complex conjugate is also a 0, turn that into a factor as well. Multiply those together and you'll get a new polynomial. Divide that polynomial by the original to find the last factor. Turn that factor into a 0 and solve for x. We've got one last problem to try. If they tell you that negative 1 is a 0, find all the others, and then they give you a polynomial. So we have a 0 that they're given to us, so let's turn that into a factor. Remember that zeros and factors are always opposite of each other. So if negative 1 is a 0, x plus 1 is going to be a factor. I'm going to take that factor and divide it into the polynomial that I'm working with. Now this time I didn't do the conjugate because this is not imaginary. If it was negative 1i, I would have had another factor that I could have found. But they only give me one, so I'm just going to go with what I've got. So now I'm going to do long division. X into 4x cubed is going to be 4x squared. 4x squared times both of those is going to be 4x cubed and 4x squared. Now I'm going to subtract. 6x squared minus 4x squared is going to be 2x squared. Bring down the next one, positive 5x. X times what is 2x squared? That's going to be 2x. Multiply 2x by both of those, I get 2x squared and 2x. Now I'm going to subtract. First two are going to cancel. 5x minus 2x is 3x, and then I bring down a 3. X times what is 3x? That's easy. That's just a 3. 3 times 1 is 3. 3 times x is 3x. Luckily, when we subtract, we do get 0. We ended up with no remainder. So let's look at what we got. We have 1 0 that we turned into a factor. We divided that factor into the polynomial, and we got this. There are 2 more zeros hidden inside here, and I can tell that because it's a degree 2. So to get those 2 other zeros out of there, we're either going to need to factor this using reverse FOIL or the Xbox method. If we can't do that, then our only other option is to do the quadratic formula. So when in doubt, if you can't factor, the quadratic formula is another choice. Hopefully students remember it from their 2 years of algebra. You're going to list out A, B, and C. A is 4, B is 2, C is 3. And we're going to do opposite of B, plus or minus the square root of B squared minus 4 times 4 times 3. 4 times 4 is 16, times 3 is 48. We are subtracting that. On the bottom, 2 times A. Now when you simplify here, you're going to get negative 2 plus and minus the square root of negative 44. Now don't panic, all that means is our other 2 answers are going to be imaginary. So let's simplify that part as much as we can. Negative 2 plus or minus, let's break that down into negative 4 and 11. The negative 4 is going to turn into negative 2 plus or minus 2i square root of 11 over the 8. I broke that up into 4 and 11 because I knew the square root of 4 was going to be a 2. The 2 comes out in front, the 11 has to stay. Let's talk about reducing now since I've got a 2 and an 8 and a 2. Let's pretend for a moment that the I wasn't there just so students can see it a little bit more clearly. Let's just pretend that it said that. The 2 and the 8 and the 2 and the 8 could reduce. So divide everything by a 2 there, and we're going to get 1 plus 1x over 4. So that's what's going to happen here, only it's not a 1, it's going to be an I instead. So this square root of 11 behaves very similar to what a variable would behave like. So I'm going to get negative 1 plus and minus I square root of 11 over 8. So those are my zeros, and it did ask me for the zeros. If it had asked me for factors, I would have needed to say x plus 1 plus I square root of 11 over 8 and x plus 1 minus I square root of 11 over 8. So I'd take each of those and do x minus the opposite of each of those. Remember that there are two answers there, one with a plus, one with a minus. But they don't ask us for factors, they ask us for zeros, and that's what these are. So we've got negative 1 plus I square root of 11 over 8 and negative 1 minus I square root of 11 over, and I forgot to divide, didn't I? That should have been a 4 there. So that 8 turned into a 4, I just forgot to write it that way. So there's my last two zeros. They gave me 1, negative 1 is a 0, and then I had two more zeros that were complex. I couldn't find them by factoring, so I found them by doing the quadratic formula. Students need to know that if you could have factored this, that would have been faster and easier to factor it instead. This one is unfactorable because it is complex when you solve it. So the complex ones, you're only going to have the option of doing the quadratic formula for those.